from our last lection. Well, let's come back to our equations. So the dissipation and conservatism models. So far, we've finished our last lection with the definition of conservative and dissipative systems. So once more, we calculate the biomass gain. That is P is the sum of our Ni with some coefficients that reflect the different size. We calculate the derivative of P, and we see that there is a linear sum and a quadruple sum. So let us focus on this last part. So if for some positive gammas the form f equals to 0, then the system is called conservative. And if it is always negative except 0, it is dissipative. What does it mean? What does it mean that the system is conservative? Our function f reflects the intraspecific and interspecific interaction. So it is the change of our biomass caused by interspecific and intraspecific interaction. So if the system is conservative, we can say that the intraspecific and interspecific interaction does not affect the biomass gain. Sometimes it can happen in economic models when the company Ni pays some amount of money to the company Nj, and Nj gains the same amount of money, so the full money gain caused by intraspecific and interspecific interaction is 0. In the real life, in biology, it means this conservative system means that the interaction do not affect biomass change. So all the interaction caused by predator-prey situation, so all the biomass go from preys to predators. So it's not that natural situation. But still, we can formulate some theorems about this situation. So it is the definition, the first for conservative system and the second for dissipative. And there was a task to prove for dissipative metrics. Next one. So, in conservative system, as I said, the interaction doesn't affect the total biomass, and in dissipative system, the biomass decreases. So it is much more natural, and if we consider any real biological system, we can expect that it will become dissipative. So the biomass gain from the first part of our P dot is balanced by the dissipation in the system. So our victims gain the biomass from the environment and then transpose it to some of the biomass, transpose to predators. And then the system will become balanced. So the conservatism for some economic models, it's okay. So there is the preservation of the total mass of funds in economics. So so the conservatism can happen in the real life. So first of all, a theorem for conservatism. If we consider the community matrix, we can prove that if AII is 0 for all I from 1 to n, and when I is not equal to j, either Aij is Aji is 0, or the product of Aij and Aji must be negative. And moreover, for any set of different naturals P1, Pm, the following equality must take place. So it means that if there is a complicated transition of our biomass, the sign must change. In the simplest situation, Aij, Aji is negative, and when there is a lot of victims and predators involved, then the last inequality must take place. So these guarantee us the transition of our biomass from victims to predators. So all of the biomass from victims is transposed to the predators' biomass. Next one from the conditions. For example, it follows that only the predator-free systems can be conservative, and these systems must be without self-limiting, or the communities of our species must not interact each other. So far, if we consider their biological models, we can conclude that there is no conservatism in the real life, since the conservatism needs equalities. And we discussed the situation that there are no exact equalities in the real biological systems. But in economics, for example, it's okay because these equalities can hold due to the rules of money and some other funds transfer. Next one. If the community is conservative, and the condition 34 is satisfied, the condition 34 is this one. So the condition for the populations that do not exist in our equilibrium. Finally, if the community is conservative and the condition 34 is satisfied, then the equilibrium state is stable. And if some of the inequalities 34 are fulfilled as strict inequalities, then the stability with respect to these variables is asymptotic. And moreover, the domain of asymptotic stability will be all our set D, where the equation have the sense. You can find the proof of these theorems in the materials that I will upload in the group. So I don't want to focus on these proofs. So just the main results, because things becomes more and more abstract, and I do not want to focus on complicated mathematics. What about dissipation? From the dissipation definition, we can formulate some necessary conditions. First of all, AII must be negative. So all our species must be self-limited. Otherwise, our matrix will not be dissipative. There will be no negative definite form. And the second one, the determinant of matrix A must be not equal to 0. So far, there is no more than one positive equilibrium in our positive quarter. So if the system is dissipative, then there is no positive equilibrium or only one positive equilibrium. And there is another condition named Sebastianov-Kotelyansky conditions. So if they are not satisfied, then our matrix will not be dissipative. And finally, if the species community is dissipative, then we can conclude that equilibrium state is asymptotically stable with the D as the domain of attraction. So if our community is dissipative, then if the equilibrium state exists, then it must be stable, and all our solutions must go to this equilibrium. So far, if it is really a big result, we see that if the matrix satisfies the dissipation conditions, if the matrix is dissipative, and if the state of our equilibrium exists, then it will always be stable. A task for you: can you give me some examples of the system that are neither dissipative or conservative? First of all, give me an example of a dissipative system and give me an example of conservative system.
I think I know one example of conservative system. It's Sun system, no? Our university?
No, from the mathematic point of view.
From mathematic.
So we consider some matrix A such that the conservative such that there can exist a set of positive gamma 1 gamma n such that this sum is always equal to 0. We can just consider 2 by 2 matrix, or maybe something more simple. Can you give me an example of this system? So what Aij we must pick to ensure that the system is conservative? There is two very simple models with the conservative system. And I'm not sure that our solar system is dissipative or conservative. First of all, because it is not derived by our Volterra equations.
I agree. Yeah.
The equations are a bit more complicated, and I'm not sure that that the energy in this system is conservative, because, for example, the sun emits energy to space, and so the whole amount of energy in the solar system, I think it is also dissipates. And the system itself is much more complicated.
Okay, let us consider identity matrix. Maybe we can find this.
Okay. If we consider identity matrix, then our form, our sum, will be gamma I plus AII and I square. So it can be zero only if AII is also zero.
Yeah, they are not positive.
But in this situation, it is real conservative system if all the coefficients of our matrix is zero. Then we can conclude that it is definitely conservative for any gammas, for any possible gammas. It is always conservative. So if our species do not interact, the system is conservative. It's quite natural. Another simple model, we considered Lotka-Volterra equation. We have seen that all the biomass of our victims was transited to our predators. So if we consider skew symmetric matrix like 0, 1, negative 1, 0, with gamma I equal to 1, we can see that this sum is n1 and 2 minus n1 and 2. So far, these metrics will be conservative.
Understandable.
Yes, and we can see that the sufficient conditions are met here. So in the simplest case, AII is 0, and AII and AIJ AJI is negative. So the product is negative. And if we consider the set 1, 2, we'll see A1, 2, A2, 1. Oh, no. There is only one. All this product is only one. So A1, 2 is negative A2, 1. So far, our simplest system is met the sufficient conditions, and so we can see that necessary and sufficient conditions. So both of them are met for this simplest case. So it is for conservative system. So we can see that the predator-free models with full transition of biomass are conservative. So far, they are stable according to our theorem. And we have seen it for two-species interaction. We saw that the predator-prey model with no self-limiting is stable, but not asymptotically stable. And the same as our theorem. So the equilibrium state is stable. And there is no condition 34 for our case because all the coordinates of our equilibrium is positive. So another question. Give me an example of dissipative system. So these sum will be always negative.
It must be something minus something squared, and it must be always negative.
What about the matrix Aij?
Yeah, this is not trivial.
Yes, there must be some negative squares here. The simplest way to achieve these negative squares is to consider the system equals to negative identity matrix.
Mm-hmm.
So far, Aij, the only non-zero remaining Aij is Aii. They are negative. So n, this sum is just a sum gamma I, Aii, and I square. And if Aii is negative, then all the sum will be negative 2. And it is a negatively definite quadratic form. So the negative identity matrix will be dissipative. So that's all about dissipation and conservatism. We can check a matrix for dissipation and for conservatism. There are some quite simple necessary conditions for dissipation and simple necessary and both necessary and sufficient condition for conservatism. So we see that this interaction type, so the interaction type itself give us the answer is the equilibrium state is stable or not. But there is the last question. So let us consider our equation 29, this one. Let us suppose that the equilibrium is positive. So all Ni are positive. Just a moment. So we consider non-singular matrix with a non-zero determinant. It guarantees us the existence of a single positive equilibrium. It guarantees us the existence of a single equilibrium. And in addition, let us suppose that all the species survive. So we consider the situation when all the species survive, so all the coordinates of our equilibrium are positive. Usually, if they do not survive, we can consider another system when there are, with the extinction of these species that did not survive, and we consider small equation. So then the equation for our coordinates is derived by equation 39. So Ci plus sum of ai, j, and j tiled is 0. That's why the coordinates of our equilibrium depends on Ci and depends on aij. Next, let us consider the linear approximation in a neighborhood of our point n. So let us consider xi is ni minus ni tiled, and make the variable change in the equation 29. We'll get the linear approximation and some form of the second order. So far, the stability of our equilibrium point depend on the eigenvalues of these matrix. Let us consider the matrix itself. It is our matrix A, and we multiply it by diagonal matrix consists of ni tiled. So we can rewrite it in this form. The D is a diagonal matrix and A is our community matrix. In our situation, we consider matrices D with positive diagonal elements. And finally, the equilibrium position is asymptotically stable when the eigenvalues of our matrix dA lies in the left half plane of the complex plane. So finally, it is the what is the reason of this problem? What's the idea of this problem? Our point n tiled depends on coefficient Ci, and we usually do not know these coefficients for real-life models. And if the matrix dA is always stable for any positive matrix D, then the stability of all our system depends only on the community matrix. And we'll see that for some community matrix, these conditions are fulfilled. So far, the type of the interaction ensures us the stability. There is some series of theorems. Will not prove them. They are really complicated. We just consider the final result of it. First of all, a task for you. Consider the case n equal to 2 and prove that that the stability of matrix A does not imply its destability. What is destability? If the matrix DA is stable for any positive diagonal matrix D, then we call the matrix A D stable. So far, not every stable matrix A is D stable, and you can see and you can prove it. It's not that complicated. You just just derive the stability conditions for matrix A and for matrix dA, and then you can find the matrix D so that the matrix A satisfies stability conditions. All the eigenvalues of the matrix A is in the left half of our complex plane, but the product dA, the eigenvalues of the product dA can be positive. So the real parts can be positive. It's not that complicated, just you need to write the conditions, write down the conditions. So far, what about the theorems of the d-stability? There is a theorem. A stable matrix A is d-stable is if and only if for any matrix D, for any positive matrix D, polynomials, real part and imaginary part of this determinant are mutually simple. Here I is an imaginary unit and E is identity matrix. Maybe I should better use I for identity matrix. Well, it is extremely complicated and absolutely impossible to use. So it's just the theoretical result. And in practice, I don't think one can use it for even for simple matrices. So it's just the algebraic theoretical result. That's why there is a number of theorems for sufficient conditions. So if these conditions are fulfilled, then the matrix A is d-stable. So first of all, there is a necessary condition. For a matrix A to be d-stable, it is necessary that all its principal minors of even order are non-negative and the odd ones are non-positive. And there exist non-zero principal minors of each order. So it looks like the condition of negative definite matrix A. Next, some sufficient conditions. Sufficient conditions for our d-stability. First of all, if the matrix is dissipative, a matrix is dissipative, then it is d-stable. So if the community is dissipative, then if in the community exists the positive equilibrium, it will be stable. Next one, the matrix A must be stable and have non-negative off-diagonal elements. So Aij must be non-negative, and Aii must be negative. It is the necessary condition for sure. Next one, the matrix is triangular with negative elements on diagonal. And finally, the matrix is 3-diagonal and the principal minors of negative A are positive. So just the theoretical results. Sometimes we can use it for real matrices. We'll see an example. So if any of these conditions is fulfilled, it ensures that our community is d-stable, so it's very, very stable. An example. We consider a system when every one of them is a predator, both is a predator and a victim. So let ith species feed on I minus first, and it is food for the next one. So far. Every our species is the predator. So I minus 1 is positive because the next one is a food, and I plus 1 here must be negative. And the very first species, is our well, it is the total victim. So it is the start of the food chain. And all the next are both predator and preys. And the last one is a total, the main predator. The main predator, because it hunts n minus 1 species, the population n minus 1. So far, will this system be stable or not? If we write down the matrix of this system, we'll see that the matrix is 3-diagonal with AII on diagonal and AI minus 1 to the left of the diagonal and AI plus 1 to the right of the diagonal. Let's suppose that the system have the positive equilibrium position. If we calculate the matrix of the system, we can choose gamma 1, 1, gamma I plus 1 is gamma I multiplied by AI I plus 1 divided by I plus 1 I. And finally, the quadratic form f of n takes the diagonal form, and so that the system is dissipative. If it is dissipative, it is distable. And finally, the equilibrium position, if it exists for our system, is asymptotically stable. So for our predator-prey model, the main type of the interaction, so that fact that the first is the prey and all our are predators and preys, this interaction type guarantee us the stability. So it doesn't matter what is this, the value of C1, CI, Cn, and value of Aij. Only the signs of our coefficients take the influence. Only the signs. So far, for some of Ci, Aij, there is no equilibrium position, and we can't say anything about their stability because of there is no equilibrium. But if the equilibrium exists, the interaction type ensure us the stability. Well, that's all about our equation that are derived by differential equations. So next, let us turn to another types of models. We'll consider, first of all, we'll consider difference equations. Have you ever met the difference equations? The difference equations in this type. Nk plus 1 is f of nk. Have you ever seen these equations before?
Maybe when we had computed integrals in Euler form, I'm not sure. Or when we wanted to calculate the derivative of something.
It's not the derivative. It's not the derivative. It is a recurrence equation. So far, for example, let us f of nk is 2nk. Then n1 is 2 and 0, n2 is 4 and 0, or 2 and 1, and so on. So the solution of our equation will be nk plus 1 is 2 raised to k power n 0, like this. So it's not differential equation at all. It's completely different. I think every one of you know at least one of these equations. You know about Fibonacci rabbits and about Fibonacci equation. So the Fibonacci equation is nk plus 2 is nk plus 1. It is our Fibonacci equation. And in the real life, there is a huge number of these of some species communities that that have following dynamics. First of all, a question for you: when should we use difference equations in our real life? Give me an example of these species. What are these animals that can be described by these difference equations?
As you said, rabbits, no?
Well, rabbits not that good because we know that first of all, let us remember the very first lection when we considered different propositions for differential equations. First of all, the species are evenly distributed along the forest, so it is satisfied for rabbits. The number of rabbits is quite large, it's okay. Then the rabbits, they reproduce all the year. It's also okay. So far, I'd better use a differential equation for rabbits. But there are some animals that are definitely cannot be described by differential equations. So the simplest population is insect population. We know that if we consider, for example, every spring, we have different N0, N1, N2, and so on. Because their previous population lay eggs. Then in the winter, all the population dies, and there are only eggs remaining. And in spring, all our insects hatch out from eggs, and we can consider the next generation of our population. The generations are separated in time. So far, the differential equation must take into account some period when there is no population at all. And then when all of them they hatch out, then well, their solution is not continuous at that moment, because for example, in I don't know when they hatch out. I think it depends on the region. For example, in March there is no insects, and then all of them appear in April, or maybe in May. So it is absolutely different situation. We cannot consider our differential equations at all. So far, we have to consider the recurrence equations, and we'll see what happened in this situation. Are there any ideas of the stability? Is the solution of recurrence equation can be stable or not? And there is an interesting situation that we can easily solve the recurrence equations using Excel. We have to use some complicated mathematics or MATLAB and so on for our differential equations. And I'm gonna show you some recurrence equations using Excel. We can change some variables in the model, and we'll quickly see how does the solution change. So first of all, a few words about stability, about stable solutions, equilibriums, and so on. First of all, the solution of our difference equation, is a set of numbers. So if we have some initial value n0, we can easily calculate n1 is f of n0, and it is our n1. n2 is f of n1, or the same, f of n0. It is our n2, and so on. So all the sequence from n0 to infinity is the solution with the initial condition n0. So if we change n0, we'll get another solution, and we can compare the solutions that we got from close initial conditions. So the same as in differential equations, we change the initial condition a little, and then we'll see if the solution will become close to our first solution or not. So far, if another solution, I think there must be n01, because if the solution, the first and the second, they have the same n0, all the solutions will be the same, right? So here must be n0, 1. So I'm sorry for this mistake. So far, if the mean value of the difference between initial condition is small, the difference between the solutions is the same, small, then we say that the solution n0 starting with n0 is stable, and if the difference between the solutions is going to 0, then as k is going to infinity, then we call this situation the asymptotically stable solution. And neutrally stable if it is stable but not asymptotically stable. So next one. What is a steady state for our difference equations? So what is the condition for steady states or equilibriums? Are there any equilibriums in our system? The answer is quite simple. We consider our equation 33, and we suppose that nk plus 1 is nk is simply n_est for all k. So far, it's clear that the stability condition, the stability condition is n_est is f of n_est. We can compare this situation with differential equations. In differential equations, the condition for equilibriums was f of n_est is 0. That's the first great difference between differential equations and difference equations. The first one, the first main difference. Next, the solution become periodic of period p if nk plus p is nk for all k. Then the solution is periodic. And we can see that p is minimum period. Because, for example, two periodic, the periodic of period 2 will be periodic of period 6, 4, 8, and so on. So we can see the we call periodic of period p if p is minimum of all possible periods. Well, next, the graphical analysis of our recurrence equation. That's the problem, because I should show you this slide along with the next slide, the same. So I'm gonna change them from one to another. So the method is called cobrubbing, because the final result is similar to a rub that is made by spider. So the graphical analysis. So we just try to derive is the steady state is stable or not using our only the plot. So let's look at these pictures. Well, what does it mean? Here is n, n, and here is n, n plus 1. So far, the line, do you see the pointer? Do you see everything that is on the screen?
Yeah.
So it's okay. I can show you by pointer because, well, I need to open some MS Excel files and they do not go at my tablet. So far, I have no pencil and I have to use the pointer instead. Maybe I will show you all the Excel pictures and then we'll come back to the tablet for the next lection. Because I want to show you this cobwebbing in for the real equation. So what is this line? What does it mean? So it is the diagonal of our first quarter. So far, it is the line n plus 1 is n. And n, or maybe nk is nk plus 1. It is the line. And the second is the function f of nk. So this one is our right-hand side of the equation, is our function. So what are the equilibriums here? We can easily find the equilibriums. It is just the intersection between the line and the function. So in this model, we have, let's look down. We are trying to cobweb an equation. Nk plus 1 is nk exponent r1 minus nk. Looks complicated, but we'll see why it is, why we use the right-hand side in this way. So we are trying to solve the equation for different constant r. If r is 1.8, we see that this equation have only two solutions: the zero solution and the solution n is 1. We can see that really if n is 0, we have 0 to the left-hand side and 0 to the right-hand side. It's okay. So we have a trivial solution. And another one, if nk plus 1 is 1, nk is 1, here we have exponent of S0. And finally, the exponent of 0 is 1. So 1 is a 1 so far in our equation. Moreover, 1 is always the solution of our equation. It doesn't depend on the constant r. So we always have this solution. The plot, the curve for our right-hand side of the equation always intersects with the line nk plus 1 is nk in the point 1. So what about the solution? How can we solve our equation? How does we achieve these strange pictures? So let us start. First of all, we choose the starting value n0. So our n0 is n0. We begin at the point n0, n0. Where is this point? It is here. It's here. let n0 be 0.1, 0.1. Next, on the first step, we draw a vertical line to the curve nk plus 1 is f of nk. And when our vertical line reaches the curve, this is our point n1. So we started at the point n0, n0. We draw a vertical line. At that moment, our line intersects to f of nk. And this point is our point n1. Then, next, we draw a horizontal line to our line. At that moment, we get 0.5. So far, our n1 is this line. So on the second step, we start with n1. The same, we draw a line. We see something like 1.2. We draw the next line, and these so n0, n1, n3. Next is the same. We draw a vertical line. Now it goes down, not up, it goes down here. Then we draw a horizontal line to our line. And so this is our point n4. And when we continue this situation, this process, we get n0, n1, n3, n4, n5, n6, n7, and so on. And we'll see that this drawing is going to our equilibrium. So far, we see that this solution, starting at this point, is going to an equilibrium. And this equilibrium is, for this situation, it is stable. When the curve in the right-hand side is different, for example, like here, or here, or here, for different R, we'll see the different picture. For example, if R is 2.2, we see some oscillations because the solutions are going from this to this, from 0.5 to 1.5. And when R is become greater, then something strange is happening. We see that there is no exact dynamics. It's really hard to understand what's going on. We'll further see how to analyze these models. And when R is greater than, we increased R furthermore, we see some chaotic dynamics. The dynamics becomes very strange. Let us see this solution. So let's see what is happening. We are trying to solve our equation. Do you see the Excel file?
Yes.
Okay. So what do we see here. The blue dots, it is our line xk plus 1 is xk, and the yellow line, it's close to 0. That's why we don't see it. But oh, no, like this. So it is our right-hand side of the equation. The right-hand side. There is something strange. Because they do not intersect. Why they do not intersect? What's going on? Is it okay with my equation? Well, it seems that yes. What happens to our equation? It is the solution. It's the solution. We see that we start close to 0. It is the first, the second, and so on. So we see that in 10 steps, the solution becomes very close to 1. And then he remains close to 1. Next, let us increase our R. Let us increase our R. We see that the solution stabilizes much quicker. There is no oscillations at all, no oscillations. And the solutions are quickly approaching our stable point. For sure, we can solve this equation for different x0. For example, we can solve it for this one, and we'll see that the same. If we start far from 0, it still stabilizes near 1. So in this model, the system very quickly stabilized near the 1. So it is the result of our observing. Unfortunately, I can't draw the observing with the lines, but here we can see the result of our observing. But next, what will happen if we will increase R more? We see that R becomes more than 1, and what have changed? The change is little, but we see that there is a very small oscillation here. It's at the 4th step. The solutions exceed 1. So the oscillations start here, but they quickly vanish, these oscillations. Let us increase our R furthermore. We see that oscillations become more strong. They become more and more strong. And moreover, the line, our right-hand side of the equation, now intersects the line xk plus 1 is xk. So at that moment, the intersection there is another steady state, but it is unstable now. But what will happen if we gonna increase R furthermore? We see that there are strong but decreasing oscillations. The bigger is R, the bigger are the oscillations. And finally, when R is close to 2, the amplitude of oscillations is still decreasing, but the solutions oscillate. When R is 2, they are still oscillating, but if R becomes greater than 1, we see that oscillations become stable. So for 100 of steps, there are oscillations. And the solutions oscillate between 0.6, it's here. Well, it's a bit strange because there must be intersection in these oscillations. Is it the right f of n or not? It looks a bit strange because there must be two intersections. There must be two intersections. Well, I think there is a mistake in this first plot. A bit strange because intersections here must be seen here. Well, I think it's just the mistaken plot in the right hand side. Still, there are some oscillations when R is greater than 2, and when we increase R furthermore, we'll see that oscillations become unstable. Something like this. But still there are some close maximums, but there is no stable state here. And if we furthermore increase our R, we'll see that the chaotic still the chaotic solution. Well, just a moment. I'm gonna look. Maybe I have better model. Just a moment. Maybe there is a better model. Where is it? Let's find another. Okay, another model close to previous one. Well, I'm sorry. It is the picture. For a steady state. But in this situation, we do not have a steady state. We have a 2-point cycle because the system goes from here to here, here to here. So it is the cycle, and there must be another plot. We'll discuss it a bit later. Well, it is our solution for this model. Well, we have to talk a bit about the mathematics. We still can analyze our stable states. We can analyze their stability. We can see that this analysis is very close to our linearization in differential equations. Let us remember how do we linearize the equation in differential case. We considered the new x equal to n minus n est, and we were trying to find the linear approximation near our steady state. Let's do the same for difference equation. So let n is n small, n minus the equilibrium. Nk plus 1 is f of so nk plus 1 is n small k plus 1 minus n est. So nk plus 1 is f of n est plus nk minus f of n est. Then, when we linearize the function f of nk near the point n est, we have the constant term f of n est. So this one is f of n est plus f prime at n est multiplied by nk plus high order terms. So far, the linear approximation for our difference equation is the same. We get the linear part and the high order terms. Let us assume that nk is small and we can neglect high order terms. So we just consider only the linear approximation equation. Let us see what can we do with the linear approximation. In the differential equations, we consider the matrix, the eigenvalues of our matrix. But now, in the difference equations, we can just give the exact solution of the linearized equation. Just because f of n est is a constant. So far, the general solution of our linearized equation is nk is n0, f prime of n est raised to kth power. So far, the since n is the difference between n and n est, if it remains small for k going to infinity, then we can conclude that the equilibrium n est is stable. Or if n is going to 0, then equilibrium is asymptotically stable. So the same logic as in differential equations. So far, we see that the stability of our equilibrium n est is derived only by the value of f prime. Let us analyze f prime. We understand that if the absolute meaning of f prime is greater than 1, then it will increase with increasing of k, and otherwise it will decrease. Moreover, the sign of f prime guarantee us the oscillations if it is negative, because the sign will change all the time with increasing of the k, or if the sign is the positive, then the stability or instability will be monotonous. So finally, we can conclude it in the next slide. Let lambda is f prime of n est. So the trivial steady state, so the steady state n equals to n est, the steady state is oscillatory unstable as lambda is less than -1. So it changed the sign and is not going to 0. Oscillatory asymptotically stable as lambda is greater than -1 but less than 0. Monotonically asymptotically stable as opposite lambda is greater than 0 but less than 1. And monotonically unstable as lambda is greater than 1. So far, for our difference conditions, for our difference equations, the stability condition is absolute meaning of f prime at the equilibrium is less than 1. So we can compare it with the condition for differential equations. For differential equations, the real part of eigenvalues of f prime must be negative. And here, the mean value must do not exceed 1. So the same for our initial equation. We see 3 bifurcation positions. There is 3 bifurcation points. -1, when the behavior of the system changed from oscillatory unstable to oscillatory stable. 0, when the oscillations are replaced with the monotonically stable behavior, and then when lambda cross 1, then stable solution become unstable. And as in differential equations, when lambda is plus or -1 at that point, and that point, we can't say something about the stability because high order terms take the influence. They take the influence. Well, I think that's all without our introduction to difference equations. The next lection will try to analyze some of the difference equations, and we'll see the conditions for our, for example, Ricker equation when our solution 1 was stable or unstable. We'll see that we can derive it from this condition. Then we'll see that there are some 2-period solutions And these two-period solutions, the same, they can be stable or unstable, and still we can analyze it. So we can analyze their stability. Well, that's all about today's lection. I would like to ask you, are you ready with your presentations now? Because there was nobody in the Google Docs. So what about the presentations?
Actually, we can in our table who was preparing. Let me see.
It was nobody in the morning. I checked it.
Yeah, this means that today I think nobody can show us something.
Well, it's a pity because we don't have too much time left. And well, so if anyone wants to pass the examination and get a good mark, he must present something. So
can I ask a question?
Yes, sure.
Does making presentation apply to all of us or only to the practice group?
To the practice groups, but well, there is a group when well, I am the lecturer for all the groups, but practice is divided. If I'm not your professor for practice, so you make your presentations for another one. And if I'm your tutor for presentations, so you must do presentation for me. So I don't remember what group is mine and what is not mine. As far as I remember, the fifth group is not mine, and all others are mine. But every one of you must do something at the practice. For me or not, but any one of you.
Yeah, thank you. I understand.
Okay, so we have a few practices or workshops more. So I ask you to hurry up because you'll be short in time. You can't make 20 presentations during only one class. One presentation is 20 or 30 minutes, so you have to hurry up because only 5 or 6 presentations were made, and there are like 40 or 45 remaining students. So hurry up. We'll not have time for all of you. So see you on Monday, and try to prepare something. You have the timetable, the Google document. So fill it with your surnames and the name of the presentations, and hurry up. So if no one is ready, that's all for today.
Okay, bye.
Thank you for attention. Yes, if you have you any questions about lections? If you have, you can ask. Well, okay. See you on Monday.